Hello, this is Math Jazz from Almost Cool, and I am doing another calculus review right now. So, let us look at our first problem. Our first problem is going to be, to find the limit as x goes to infinity of the square root of x squared plus 1 minus x. Limit rewrite that for guys, a little bit of technical difficulty. Got it though. Okay. Limit as x goes to infinity of the square root of x squared plus 1 minus x. So, notice if we just tried to plug in infinity, we would get this is an infinite term, and that's an infinite term, so we'd get infinity minus infinity. That is not a determinate form, so we have to rework this and try and find a new form to put this problem in that will give us an answer as to whether or not this converges. So, with this type of indeterminate form, what seems to work nicely is to multiply by the conjugate. So we're going to take this and we're going to multiply by the conjugate, which is going to be the square root of x squared plus 1 plus x. And if you notice, I didn't write that straight in line with this expression here, because when you multiply by something, you're going to have to multiply by that thing over itself so that you don't change the value of your limit. So x squared plus 1 plus x. Oh, and if you were confused by the term conjugate, all a conjugate is that we take this sign here, in this case it's a minus sign, and we flip it. So if this were a plus sign, then this would be a minus sign here, and vice versa. Whatever we put on the top, we have to put on the bottom to make the fraction the same, so we're not changing the value of the limit. Okay, so with that, we will continue onward. So now we multiply the tops out, and this is going to multiply really nicely because conjugates have lots of terms that cancel out. Namely, this term times this term will cancel with this term times that term. So what we're going to end up with is x squared plus 1 minus x squared when we're all said and done with the top. The bottom, of course, is just being multiplied by 1, so it doesn't change. And what we're going to notice is that these x squared terms will cancel, and we're left with a really nice limit to take, which is the limit as x goes to infinity of 1 over the square root of x squared plus 1 plus x. Now notice if we let x go to infinity now, what we get is infinity here plus infinity there. That's, if you take a really big number plus another really big number, it gets even bigger. So the denominator goes off to infinity. 1 over infinity is 0. So this limit is 0. Okay, so that's not so bad. So let's take a look at our next problem. Our next problem is going to be the limit as x goes to infinity of x ln x over x squared. So that looks like this. This limit doesn't look like it should be too bad either. We automatically get some really nice cancellation going on. I'm going to pull my colors up over here. So we already can cancel out an x from the top and bottom. That's going to give us a new limit of, the limit as x goes to infinity of ln x over x. Now the top goes to infinity and the bottom goes to infinity. Now if you knew already, polynomials dominate logarithms in the asymptotic case. If that didn't make any sense to you at all, polynomials go to infinity faster than logs. So this is going to go to 0. We already can tell that if we know just that polynomials are stronger, let's say, than logs. But let's prove this using, let's use L'Hopital's rule. Since we have an infinity over infinity form, we can use L'Hopital's rule. We take the derivative of the top, we get 1 over x. We take the derivative of the bottom, we get 1. The top goes to 0, the bottom is a constant, and we get 0. So that was just by using L'Hopital's rule. Now, can we use the fact that polynomials dominate logarithms on exams? No, but at least we, if we're familiar that exponentials are always more powerful than polynomials are always more powerful than logs, we can at least kind of get an idea of where things should go so that we can do the math steps correctly to get to that point. So this was not a too hard of a problem. Okay, so let's go look at our next question, which let's see. This is going to be we're going to compute the integral from 1 to 2 of, there you go, the integral from 1 to 2 of x over square root of 9 plus x squared dx. Okay, so we have this limit that we want to compute. And the first thing that we are going to think is we're going to think u substitution. Now, we have an x on the top, we have a square root of something on the bottom. We're going to do u equals the inside of the square root because it seems like that's a chain. U substitutions are the opposite of the chain rule. So what we want to do is we want to find a chain and try and undo it. So let's try letting u equal the inside of this chain. That's going to be 9 plus x squared. That makes du equal to 2x dx. We have an x and a dx on the top, so that makes us feel pretty good that we might have made the right choice. We want a 2, so let's multiply by 2. But if we're going to multiply by 2, we also have to divide by 2 to balance everything. So there's our 2, there's our negative 2, and notice that this is du, this is u, and we can now do our u substitution. So this is equal to the integral, or 1/2 of the integral, of du over the square root of u. Now, we have x endpoints here. That's x equals 1 to x equals 2. This is a u integral, so we're going to need u endpoints from u equals something to u equals something else. So what we do is we plug 1 and 2 in for x into this equation right here. And that will give us our new endpoints. So let us do that. We get u is equal to 9 plus 1 squared equals 10. So this endpoint is 10. The bottom endpoint was a 1. We plugged it in for x. We got u equals 10. So the bottom endpoint in our u integral is a 10. Now we're going to take the top endpoint and do the same thing. U is equal to 9 plus 2 squared. That's 13. That's a 13 up there. And now we can compute this limit, or so this integral, which is going to equal our original integral. That's not too bad. we get 1/2 of the integral for, sorry, we're evaluating the integral now. So this is u to the negative 1/2. We add 1 to the power, we get u to the positive 1/2. We divide by the 1/2. This is our integral that we evaluate from u equals 10 to u equals 13. That's not so bad. So I guess in slow motion, let's take a look at that. We have 1 over the square root of u is equal to u to the negative 1/2 power. We're going to add 1 to the power when we take the integral. So that's now 1/2, because negative 1/2 plus 1 is 1/2. We divide by the new power. But dividing by a fraction is the same as multiplying by its reciprocal. So this is how we get our antiderivative here. Okay. So now that we have our integral there, we notice that these 2's cancel. We plug in 13. This is going to be the square root of 13, because that's our top end point, minus we plug in our bottom end point, the square root of 10. And this is our answer. But it's not too bad. Not bad at all. Okay, so now we look at our next problem, which looks like this. Okay, we have this word problem that we're going to look at, and it's fairly long, but we can do it. Okay, it says, you own an emu ranch and want to build a rectangular fence around your herd. I don't know if if a group of emus is a herd. I think it's a flock, because they're birds. Anyway, one side of the fence must be built along the side of a river so the emus have access to fresh water. That's probably not correct, like from a keeping emus perspective, but you know, we have fun writing our problems in the math department. You want to enclose at least 1,000 square meters. The fencing material costs $6 per meter, but the fencing along the river costs $10 per meter to allow the emu to drink the water. What are the dimensions which minimize the cost of your fence? What is the cost? Okay, so what we want to do is we want to draw a diagram. So here's our river. And here's our fence. There we go. Here's our river, here's our fence. Maybe I'll like color the river a little bit. That looks like a river. Okay, so we have this side here, which is x, this side here, which is y. We know that the area of this is equal to xy. We know the cost of this is equal to something that we'll need to look back at our problem to get. Notice that it says that fencing material is $6 per meter. So, when we look at this, we know that this side is $6, and this side is $6. This side is also $6. So the cost already is going to be 6 times 2x plus y. That's going to be just this side, sorry, these three sides of the pen. The other side, when we go look at our question again, let's see, is $10 per meter. I guess that's, so that must be more complicated because that side has to allow the emus the ability to like look through and grab water, but also still keep the emus from jumping in the river and escaping. So that side is 10. So what we know is that this is going to be 10y. Okay?
Now, we also know that the we're looking for the minimum cost. We're going to assume that the minimum cost is when we have exactly 1,000 meters enclosed. So we're going to say that the area is equal to 1,000 square meters. And here we have our equations. I'm looking at the, there we go. Okay, so we have up here is $10 per meter of fence on the side of the river, $6 per meter of fence on the other three sides. The cost is going to be 6 times the number of meters for this side of the fence, and then 10 times the number of meters for that side of the fence. So here is our setup. We know that the area has got to equal 1,000, and so we can use this to solve that y is equal to 1,000 over x. We could plug that into this cost equation. Now the cost at some point x is equal to 12x plus 6,000 over x plus 10,000 over x. We're just substituting in for y. Okay, we're going to scroll up a little bit just to so a little more space. That gives us a cost derivative of 12 minus, well, 16,000 x squared using the power rule. We set this equal to 0 to find our critical points. That gives us 12 equals 16,000 over x squared. Gives us x squared equals 16,000 over 12. You can cancel out a 4 from this. Get 4,000 over 3. And that doesn't simplify anymore, so 4,000 thirds. Now we take the square root. Okay. We're going to move a little bit this way and start a new column. So x equals 4,000. The square root of 4,000 is not a great number. Well, we get a 2 times a 10 times the square root of 10 over 3. Square root of 3. There we go. This is our value for x. And we want to know the dimensions. That'll give us y equals 1,000 over 20 root 10 over 3, which is going to be 300 over 2 square root 10, or 150 over the square root of 10, which we can actually still simplify to 15 square root 10. That'll work. Those are our dimensions. Now you're wondering, how do we know this is the minimum? Well, we haven't actually checked that. We know it's the critical point, but we don't know if it's a minimum or a maximum or neither. But we can check using, say, the second derivative test or the first derivative test. So, whichever one you pick, it'll work just fine. I'm going to do the second derivative test because I don't think that this derivative will be very hard to take. So c double prime of x is equal to, well, derivative of 12 is 0. Derivative of negative 16,000 over x squared is going to be positive 32,000 over x cubed. Hey, look, this is a positive number. When I plug in a positive number here, I get a positive number. So this here, derivative is, in fact, positive. Positive second derivative means minimum. That is terrible ass. There we go. So we found the dimensions, and we proved that we have a minimum value for the cost. Now, for a multiple choice question, you probably don't need to worry about proving that it's a minimizer. So I would say this part here is only necessary if you're doing a free response question. You should do it, though, if you're doing a free response question, because the grader can dock you for missing this step, and probably will and probably should. Even though they asked you to find the minimum, there's only one critical point. Obviously, we wouldn't ask you to find a minimum value if there were no minimum. So, and we also know that all the minimum has to happen at a critical point. So if you found the critical point, you must have found the minimum. But you should still prove that you found the minimum if you're doing a free response question, because the grader is totally justified in docking you points if you don't prove that you had a minimum. Anyway, the next question we have is going to be to find the derivative of f of x equals 2 to the x to the natural log of x. They put parentheses there to make sure that you know exactly what is being exponentiated. So we have this f of x. Did I not scroll down? I did not scroll down. That's okay, though, because you can see it now. Okay, so this is our function. We want to take the derivative. Now, because we have a variable in this location and this location, that is the base and the exponent, I guess that location, we cannot use either the power rule nor the, we can neither use the power rule nor the quotient rule, the power rule nor the exponentiation rule to take this derivative. Exponent derivatives work when this is a constant. Power rule works when this is a constant. If neither of them are constant, you can't use either rule. So we're going to have to do logarithmic differentiation. So first we take the natural log of both sides, ln of this and ln of this. Exponents inside of a log can come down as coefficients. So we get ln f of x, that's the left-hand side of the equation, equals ln x, that's the exponent, natural log of 2x. Now from here we can take the derivative of both sides. This side is a chain rule. It's f prime of x over f of x by the chain rule. If you need me to do that slower, say that in chat and I will do that for you. If you don't need me to do it slower, I'm just going to move on. So we get f prime of x over f of x on that side. Here we have a product, so we take the derivative of the first function times the second plus the first function times the derivative of the second, which is going to be so natural log of 2x. We get 2x in the denominator, 2 in the numerator, because 2x is the argument, goes in the denominator, and then the derivative of 2x is 2, and that goes in the numerator. So this is how we get, this is our derivative. 2's will cancel, so goes to 1. And now what we wanted was f prime of x. What we got is f prime of x over f of x. So what we are going to do is we're going to multiply both sides by f of x and cancel. But we also know that f of x equals 2x raised to the ln x. So we canceled the f of x on this side, we multiplied by f of x on this side, and we get our final form of the derivative. F prime of x equals ln 2x over x plus ln x over x times 2x to the ln x. Not so bad. We could combine this. Like, this came out really nicely in that we could combine these together into one fraction. But I'm not going to. That's not calculus anymore. It's just algebra. So anyway, let's look at our next problem. So our next problem is going to be sketch this curve. That is a gross problem. Curve sketching is pretty terrible. Anyway, we have the function x squared minus 1 over x times x minus 2. We want to label all asymptotes, intercepts, local maxes and mins, and any inflection points. So the first thing we're going to do is we're going to find all of those things. Ooh, okay, so I guess the first thing I want to do is I want to find where this thing has zeros. I know we weren't asked in the statement to find the zeros, but if we're actually going to sketch the graph, finding the zeros is going to be helpful. So if we factor the top, we get x plus 1 times x minus 1. We notice also we have an x and an x minus 2. So I'm going to draw a number line. And what's going to happen is we're going to have marked off 0, 1, 2, and negative 1. These are zeros, and these are asymptotes. I guess ASP is as good an abbreviation as anything. Because 0 and 2 are roots of the denominator that are not balanced by corresponding roots of the numerator. So we know we have asymptotes there and there. We know we also have zeros where we have zeros in the numerator, and that'll be useful for us. So the next thing that we'll want is to find the well, we already found the vertical asymptotes, so that's good. Now we want to find the horizontal asymptotes, if there are any. Well, rational functions whose numerator is equal or lesser power than the denominator have asymptotes. Horizontal asymptotes, that is. So, since we have degree 2 on the bottom, degree 2 on the top, we're going to have a horizontal asymptote. Where does that happen? It's going to be the coefficient of the top leading term divided by the coefficient of the bottom leading term. In this case, 1 divided by 1. So we have horizontal asymptote at y, sorry. Horizontal asymptotes are y values. Y equals 1. So we found the zeros, we found the vertical asymptotes, we found the horizontal asymptotes. Oh, we were asked to find intercepts. Oh, that's totally great, because that's useful for plotting the graph. We found the intercepts, we found the asymptotes, we need the local maxes and mins, so we're going to need the derivative for this. Now, this would require us to do a product rule and a quotient rule if we wanted to do it that way. I think logarithmic differentiation is the way to go here. So we're going to find the derivative using the logarithmic differentiation technique that we did in the last problem. So ln f equals ln x squared minus 1 minus ln x minus ln x minus 2. That's not so bad. We just use the properties of logarithm. Multiplication becomes addition. Division becomes subtraction. So since we're dividing by x and dividing by x minus 2, that becomes ln x and ln x minus 2. Just do that. Take a derivative. We get f prime on the top, f on the bottom equals 2x x plus squared minus 1 minus 1 over x minus 1 over x minus 2. Here's our derivative. We multiply both sides by f, which is going to be x squared minus 1 over x times x minus 2. And multiply by f on that side. Now we have our derivative. So that's not too bad. We'll want to simplify this so that we can actually find the roots of this thing. So let's see. Let's see. We will want to combine this. We'll get 2x minus combine these two next. Get x minus 2 plus x over x times x minus 2. Let's see if I did that right. We factor this negative 1 out in front, and we have 1 over x plus 1 over x minus 2. So we need a common denominator. We multiply by this by x minus 2 over x minus 2 and x over x. We get x minus 2 times 1 and x times 1. We add them together. Okay, so we get this. And that's correct. And we'll scroll down a little bit. Okay, so now we yep. So now when we multiply through, we get 2x over x times x minus 2 minus 2x minus 2 over x times x minus 2 times x squared plus or minus 1 over square these. So this term times this one, the x squared minus 1's cancel in the top and bottom, leaving just this top and this bottom here. And then this times this, tops multiply straight across, bottoms multiply straight across like so. We need to combine for a like denominator, so we get multiplied by x and x minus 2 here on the top and the bottom. Now we have common denominator. We can combine 2x squared x minus 2 minus 2x minus 2 times x squared minus 1 over x squared times x minus 2 squared. We have this. And we'll want to combine the top terms so we can get zeros. Getting a little crowded here, so I'm going to erase just a little bit. Let's see. There we go. Okay, so we've cleared out a little bit of space, and we will continue with our manipulating this derivative. We get 2x cubed minus 4x squared minus 2x cubed plus 2x squared plus 2x minus 2 over x squared x minus 2 squared. Maybe I should clean up that fraction mark. Okay, and then we combine this term cancels with this term, and we get, it's like negative 2x squared plus 2x minus 2 over x squared x minus 2 squared. And that top, does it factor? No, it does not. Okay, so from here we have no factors in the top. We only have the 0 and the 2 factor on the bottom. So our critical points are 0 and 2, because those are the places where we do not have a derivative. Double check that. I want to make sure this has no roots. We have this, we can factor out a negative 2. Get negative 2 times x squared minus x plus x, sorry, plus 1. Does this have any roots? Well, we use the Pythagorean, we use the quadratic formula, so we get negative b plus or minus the square root of b squared minus 4 times a times c all over 2a, which is going to be 1 plus or minus the square root of negative 3. This has no real solution. Like I said, it didn't factor. We're only doing real variable calculus right now, so we don't have to worry about complex numbers in this calculus class. So this has no root in the top. The only critical points are at 0 and 2 where we have an undefined derivative. Okay, so what does that mean? And we knew that we had to have an undefined derivative at 0 and 2 because we have asymptotes at 0 and 2. You can't have a derivative at a place where you don't exist. Okay, so what do we know? We know that okay, so I'm going to draw a number line. Here's our number line for our derivative. Here's our number line for f. We have an asymptote at 0. We have an asymptote at 2. We have no other places where we can change signs. So what we know is that this polynomial is positive everywhere because it has no roots and has a positive leading term. We know that these are even-powered roots. We know that this is a negative number outside of the fraction. That tells us that we're going to have a negative value for our derivative here. When we hop over 2, we look at our root for 2. It's even. So when we go from this region to this region, we do not change signs because the power here is even. When we hop from this region to this region, we don't change signs either because this is an even root, so this is negative. So our derivative is always negative, except at the places where it's undefined. So what that tells us is that we are decreasing everywhere, except of course where we're undefined. Okay, so that is some more work that we'll need to clear out. There we go. Okay, so from here, we need to find the last thing, which is any inflection points. So we're going to need the second derivative. Oh, I shouldn't have erased our derivative. Well, I guess this gives us a chance to take our derivative using the quotient rule and the product rule. So f prime of x equals the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, which is a product in this case. So we have the derivative of the first times the second, which is just 1 times x minus 2, plus the first times the derivative of the second, which is 1 times x, all over the square of the denominator, x squared, x minus 2 squared. So from here, we need to simplify this to be able to take its derivative to find the second derivative. So we get, let's see, 2x cubed minus 4x squared minus 2x cubed. Let's see. Plus, okay, so we have plus 2x squared, and then have a negative 1, 2x. Okay, so plus 2x, and then minus 2. Okay, over x squared times x minus 2 squared. Now, we still get the same cancellations as before, and we get equals negative 2 times x squared minus x plus 1 over x squared times x minus 2 squared. So we have our derivative now. Now we need to take the second derivative. And let's do this using the quotient rule. We have f double prime of x equals negative 2 times the derivative of the top, 2x minus 1 times the bottom, which is x squared, x minus 2 squared, minus, so it's the denominator times the derivative of the numerator times the numerator times the derivative of the denominator. Sorry, minus the numerator times the derivative of the denominator. So we get x squared minus x plus 1 times the derivative of the denominator, which is the derivative of the first times the second, plus the first times the derivative of the second. Okay, all over the denominator squared. This was a terrible final question. I feel very bad for the students that got this. Anyway, so now we have to figure out where this thing has roots and asymptotes. We already know 0 and 2 because they were roots and asymptotes before, so they're going to continue to be roots and asymptotes now. But anyway, let's get some more canvas because we're running out of it. Guess I don't have the ability to do that. Anyway, we want to simplify. We know where the roots of the bottom are. We only really need to figure out where the roots of the top are. So we need to multiply all this stuff out. Oh my. This is going to be a 5th degree polynomial on the top. That's not cool. Okay, so we have... Oh, you know what? We are not going to do the rest of this. We're not going to find where there's an inflection point. We could do this, but this is an algebra exercise right now. All we have to do is multiply this out on the top, cancel all the terms, gather all the terms together, and then find a root. And at that point, like, it's not really calculus anymore. It's algebra. And we're not really testing you on algebra for this final. So, yeah. It's a really hard algebra question here. I'm sure that the degree gets canceled out somewhere. It's not gonna end up being a 5th degree polynomial. But, because
because of other mathematical reasons dealing with fifth-degree polynomials. It's not going to end up being a fifth-degree polynomial, I'm sure. But let's do another calculus problem. At this point, we've proved that we've done all the calculus necessary. We're going to find a root for this. That root's going to be the inflection point. Well, it's going to be our possible inflection point. We have to check to see the right and left. Does the second derivative switch signs on the right and left of the 0 for this? That would give us whether or not this is an inflection point. Anyway, so we're going to select all of this, get rid of it. It's too weird. Okay, so now we want to graph this thing. So we know here we go. So we have our graph. We know that we have an asymptote at 0 and at 2. We have a root at 1, another root at -1. We know we have a horizontal asymptote at y equals 1. Here's our horizontal asymptote. So, and this thing is decreasing always. So that means that we're going to come from our asymptote, go down to our other asymptote, because we are decreasing. We're going to start up at this asymptote, come down, cross through this point. Oh, I guess that was another thing. We come from this asymptote, we have to hit our 0 there, and then go down to our asymptote. We come down from this asymptote, hit our 0 there, go down to that asymptote. And we start up at this asymptote and go out across like that. And this is the graph of this function. I'm betting that there's a inflection point there. However, I did not bother to check because I was not going to find the zeros for that second derivative. You can do that, or you can plug it into Desmos, and Desmos can do that. I highly doubt that there'll be a question like that on a current midterm. Let me rephrase. There will be a graphing question, but the graph should not have a second derivative that is that terrible to solve for. Okay, so with that, let us move on to our next question. So we're going to use the definition of derivative to find the derivative of f of x equals 1 over x minus 1. So that's f of x equals 1 over x minus 1. We want to use the definition of derivative to do that. So the definition of derivative, if we have forgotten, I'm going to write it up over here. Limit as h goes to 0 of f of x plus h minus f of x over h. So we're just going to plug f into this. We get the limit as x goes to 0, as h goes to 0. Limit as h goes to 0 of 1 over x plus h minus 1 minus 1 over x minus 1 over h. That's not too bad. It looks a little strange, but all we're going to do is combine our fractions on the top. Limit as x, it says h goes to 0 of x minus 1 minus x plus h minus 1 over x plus h minus 1 times x minus 1 all over combining these two fractions on the top, h. But dividing by h is the same as multiplying by 1 over h, so this is the same as just going 1 over h. But that just means that we're multiplying the denominators together. So basically, the end result is that we can pull this h up into the denominator like so. That's the end result of everything. This simplifies into this. Then the next step, we're going to cancel out this x with this x, and this one with that one, and we're going to be left with the limit as h goes to 0 of negative h on the top over h, x plus h minus 1, x minus 1. The h's cancel, leaving a negative 1 on the top. This h goes to 0, leaving negative 1 on the top, and x minus 1 squared in the bottom. And for some reason, it does not seem like Desmos, or like, strange. I don't know what's happening with YouTube. Oh, yeah, it's working. Okay. There we go. So that is how we take a derivative using the limit definition of derivative. And if you notice, we did both parts of this problem at the same time. We set up the limit and we took the derivative by evaluating the limit. That was 6 points. Okay, so the next problem that we have is we want to talk about a related rate between the area of a circle and its circumference. So, let's see. We have a circle here, and we know that the area, so that's the change in area with respect to time, equal to 3 meters per second squared. We know that the relationship between the area, the radius, and the circumference is like so. Area equals pi r squared, and circumference equals 2 pi r. So we know dA dt. We want to find dc dt. So we're going to have to figure out a relationship between a and c. Well, that's not so bad. What we do is we solve for r. We get r equals c over 2 pi. And we plug this into our a equation. A equals pi times c squared over 4 pi squared. And then the squareds will cancel, leaving just c squared over 4 pi. That's not too bad. Okay, so with that, now we take a derivative. We get dA dt, that's the derivative of this side, equals 2c over 4 pi dc dt. We know this is 3, and we're looking for this, and we need to find this to solve the problem. So one thing that we do know is that we're looking at when the area is pi. So we can plug that into our area equation here. We get area is pi. That equals pi r squared. So that means that r squared equals 1, or r equals 1. Not too bad. And then we plug that into here, and that gives us c equals 2 pi times 1, which is just 2 pi. So we get dA dt equals 2 times 2 pi over 4 pi times dc dt, and this equals 3. Is what we're looking at right now. So this cancels with this, and dc dt equals 3. Okay, so that one wasn't too bad. Let us look at our next problem. So the equation, this equation implicitly defines y as a function of x. Find dy dx. So we just need to take our equation, which is e to the x plus y equals y squared, and do implicit differentiation to both sides. So we have a chain. I'm going to write some notes over here. We have e to the x as the outside function, and x plus y is our inside function on this side here. The derivative of e to the x is itself. The derivative of x plus y is 1 plus dy dx. So we plug this function into that one, e to the x plus y times 1 plus dy dx equals, this side is pretty easy, it's 2y dy dx. We want to solve for dy dx, so we multiply everything out. We get e to the x plus y times 1 plus dy dx times e to the x plus y equals 2y dy dx. This will be moved to the other side, so we get e to the x plus y equals dy dx times 2y minus e to the x plus y. And then we just divide everything by this. So that'll give us dy dx equals e to the x plus y over 2y minus e to the x plus y. This is our derivative. Okay. The next question is find the equation of the tangent line to the curve y equals e to the x times x squared plus ln x plus 1 plus 3. That is mouthful. Y equals e to the x squared plus natural log of x plus 1 plus 3. Okay, so we want to find the tangent line at the point 0, 3. From here, we just need to take a derivative. We know a point. To find the tangent line, we just need to find a slope, because we already have a point. To find a line, you need a point and a slope. We have a point. We just need a slope now. So we need to take the derivative. We get y prime equals, we're going to do the product rule here. So we get the derivative of the first times the second. Plus the first times the derivative of the second. And we just plug in 0 now. That'll give us our derivative at this point. So e to the 0 times 0 plus ln 1 plus 3 plus e to the 0 times 0 plus 1 over 1. So that's 0, that's 0, that's 0. We get 1 times 3 plus 1 times 1 equals 4. So now we know our point and our slope. That fairly weird loop that it drew there. Anyway, that means that our line
is y minus the y-coordinate, which is 3, equals the slope times x minus the x-coordinate, which is 0. So y equals 4x plus 3 is our line. By the way, this is a perfectly valid way of representing the line. It's called point-slope form. I turned it into slope-intercept form purely for aesthetic reasons. The other line also works perfectly fine as an answer. Okay, so now let us look at our next question. Okay, so actually, that was the last free response question on this exam. And we've been going for an hour now. I will come back for another hour tomorrow and do another hour's worth of questions. So I will see you tomorrow. Have a great day. Good luck studying calculus. If you have questions, please email them to me at the email address. During the live stream, of course, send your questions to, just put them in chat, or if they're hard to write into chat, take a picture and email and tell me in chat to look there. But yeah, if you have questions between now and tomorrow's live stream, then just send an email to me. If you have all of my students have all of these questions available to them. So if you have a specific one that you want me to look at tomorrow, please send me an email and I will do that problem. Have a great day. Bye.